A Japanese construction company, the same one that built the tallest tower in Tokyo, says it will build an elevator to space. Not a metaphor. A physical cable, 96,000 kilometers long, anchored to a floating platform on the equator, stretching past the moon's orbit, held taut by a 12,500-ton counterweight spinning through the void. You step inside a pod called a climber, press a button, and 8 days later you are in orbit. Cost per kilogram to geostationary orbit, $57. A SpaceX Falcon 9 charges $1,200. Obayashi Corporation says construction begins now, and the elevator opens in 2050. They are not joking. They published the engineering blueprints. They named the stations. They calculated the cable dynamics. And I did what apparently nobody in the press bothered to do. I checked their math against the actual material science. What I found is either the most exciting engineering breakthrough in human history, or a $100 billion fantasy built on a material that does not exist yet. And the difference between those two outcomes comes down to a single number that I am going to teach you in the next 3 minutes. Here is the physics you need. Every material on Earth has a property called specific strength. Its tensile strength divided by its density. Think of it as the answer to one question. How long can I make a rope out of this stuff before it snaps under its own weight? For steel, that number is about 25 kilometers, meaning a steel cable dangling from space would tear itself apart after just 25 kilometers of its own weight. The space elevator needs at least 4,960 kilometers of braking length. Steel fails by a factor of 200. Kevlar gets you to about 250 kilometers. Carbon fiber, the miracle material of modern aerospace, maxes out around 400. You are still short by a factor of 12. For 50 years, this killed the space elevator dead. There was no material on Earth strong enough and light enough to hold up a cable from geostationary orbit. The idea was science fiction, literally. Arthur C. Clarke put it in a novel in 1979, and even he admitted the material did not exist. Then, in 1991, a Japanese physicist named Sumio Iijima looked through an electron microscope and discovered carbon nanotubes, cylinders of carbon atoms arranged in a perfect hexagonal lattice, each one 50,000 times thinner than a human hair, and with a theoretical tensile strength of 150 gigapascals. That is 30 times stronger than steel at 1/6 the weight. Braking length, over 5,000 kilometers. For the first time in history, a material existed, on paper, that could hold up a space elevator. And this is the trap I am setting for you. Because that phrase, on paper, is doing the heaviest lifting of any 2 words in the history of engineering. And what I am about to show you is why. In 2003, NASA commissioned a feasibility study through its innovative Advanced Concepts program. The conclusion was shockingly optimistic. The space elevator could be built in the near future with acceptable risk and less funding than some current space programs. The key technology that needed development was the tether. The material of choice, carbon nanotubes, had the entire space elevator community celebrated. Obayashi Corporation began drawing blueprints. The International Space Elevator Consortium was founded. Conferences were held. Timelines were published. There was just one problem. Nobody could make a carbon nanotube longer than a few centimeters. I want you to feel the scale of this gap. The space elevator tether needs to be 100,000 kilometers long. As of 2024, the longest carbon nanotube ever manufactured in any laboratory on Earth is 0.5 meter. That is not a gap. That is a chasm the width of the solar system. And it gets worse. Waseda University in Japan, one of the world's leading nanotube research centers, demonstrated that growing carbon nanotube forests, bundles of aligned nanotubes, at their fastest achievable rate, would produce 1 meter of material in 186 hours. That is nearly 8 days for a single meter. The tether needs 100 million meters. Even if you could parallelize the process perfectly, the manufacturing timeline is measured in geological epochs. But here is where the story cracks open. In 2014, Google's moonshot laboratory, the people who built self-driving cars and internet-beaming balloons, began designing a space elevator. They assembled a rapid evaluation team, pulled together the world's best materials data, ran the numbers, and discovered what I just told you. Nobody had manufactured a perfectly formed carbon nanotube strand longer than a meter. Google put the entire project in what they called deep freeze, and they have never taken it back out. Okay, stop. I need you to answer something before I continue. And the space elevator needs a cable material with a specific strength of at least 50 gigapascal centimeters cubed per gram. Carbon nanotubes theoretically hit 60, but we cannot make them long enough. So here is the question. Option A. The space elevator is impossible because we will never manufacture nanotubes at scale. Option B. There is a completely different material that nobody expected, and it might actually work. Drop your answer in the comments right now. Because one of these options became reality in a Chinese laboratory in 2017, and I guarantee most of you have never heard about it. There are two camps in the space elevator war, and the fight between them is vicious. Theory A is the skeptic's doctrine. It says, the space elevator is a beautiful delusion. The material requirements are physically impossible to meet at industrial scale. Carbon nanotubes have been the poster child for 30 years, and we still cannot make them longer than a ruler. Every single defect, a missing carbon atom, a misaligned bond, a grain boundary, catastrophically reduces tensile strength. A 2023 paper in Acta Astronautica confirmed that experimentally measured nanotube strengths are considerably lower than theoretical values, with massive scatter in the data. The strongest nanotube ever tested in a lab was nowhere near the 150 gigapascals that the textbooks promise. You are not building a 100,000-kilometer tether from a material that shatters at imperfections you cannot even see. And the skeptics have an even scarier argument: space debris. The tether would pass directly through low Earth orbit, the most congested orbital band in existence. And there are currently 34,000 tracked objects larger than 10 centimeters screaming through LEO at 28,000 kilometers per hour. 900,000 fragments between 1 and 10 centimeters. And over 128 million pieces smaller than a centimeter, each one carrying more kinetic energy than a bullet traveling 10 times faster. The tether would cross every single one of these orbits. Every satellite, every Starlink bird, every fragment from every collision since 1957. All of them cross the equator twice per orbit. The space elevator is a stationary target in the busiest shooting gallery in the solar system. Now, Theory B, the believers. And they have something the skeptics did not expect. In 2004, two scientists at the University of Manchester isolated a material so extraordinary that it won them the Nobel Prize in 2010. Our graphene, a single atom-thick sheet of carbon arranged in a honeycomb lattice. Tensile strength, 130 gigapascals. Density, 2.2 grams per cubic centimeter. Specific strength, approximately 59 gigapascal centimeters cubed per gram. Right at the threshold needed for a space elevator tether. And unlike carbon nanotubes, graphene is a two-dimensional material. It does not need to be grown as a fiber. It can be manufactured as a continuous sheet, rolled out like plastic wrap, at speeds of 2 meters per minute and lengths of up to 1 kilometer. But here is the twist that flips everything. In July 2017, a Chinese laboratory achieved something the materials science community thought was impossible. They manufactured single crystal graphene at the macro scale. A single, defect-free molecule of carbon, half a meter across. Since then, laboratories in South Korea and the United States have replicated the result. The International Space Elevator Consortium pivoted almost immediately. In their February 2025 newsletter, the organization's chief architect identified graphene superlaminate, layers of single crystal graphene stacked like pages of a book, as the leading candidate for the tether material. Not carbon nanotubes, graphene. And the skeptics fire back. A half-meter crystal is not a 100,000-kilometer cable. You still need to stack thousands of layers, bond them with something stronger than van der Waals forces, which are notoriously weak, around 0.1 to 1 gigapascal, and then deploy the result through the Van Allen radiation belts, where high-energy particles will degrade molecular bonds for decades. Every grain boundary in the laminate is a fault line, and every micrometeorite impact is a death sentence. You are proposing to wrap the Earth in cling film and hang a space station from it. Now, here is the evidence that changes the equation, and this is from September 2025. A company called Hydrograph Clean Power, working with Professor Chris Sorensen at Kansas State University, unveiled a detonation synthesis process that creates graphene with over 99.8% purity. The technique uses a controlled explosion of acetylene and oxygen in a sealed chamber. What comes out are fractal graphene platelets, branched, snowflake-like structures with 200 square meters of surface area per gram. The fractal morphology means these platelets interlock like puzzle pieces, creating dramatically better load transfer than flat sheets. So early composite tests showed performance improvements of 10 to 100 times over conventional graphene at ultra-low loading fractions. But, and you knew there was a but, those gains were measured under modest stresses. Not the gigapascal range loads a space elevator tether would experience. The van der Waals bonds between graphene layers still cap practical composite strength at roughly 1 to 5 gigapascals. The tether needs at least 50. That is a gap of an order of magnitude. It is smaller than the gap that existed before graphene was discovered, but it is still enormous. And meanwhile, the space debris problem is getting exponentially worse. In 2007, China destroyed one of its own satellites in an anti-satellite weapons test and increased the tracked debris population in low Earth orbit by 25% in a single afternoon. Russia did the same in 2021, generating hundreds of thousands of new fragments. SpaceX's Starlink constellation alone performed more than 25,000 collision avoidance maneuvers in a 6-month period. The European Space Agency now estimates over 39,000 pieces of tracked debris in orbit, with the real number including untrackable fragments likely exceeding 130 million. Every year, this problem compounds. By the time Obayashi Corporation's 2050 deadline arrives, the orbital environment the tether must pass through will be significantly more dangerous than it is today. And nobody, not ISEC, not Obayashi, not NASA, has a tested solution for protecting a stationary 100,000-kilometer target from millions of projectiles moving at 10 times the speed of a bullet. Let me zoom out, because this story is not really about a cable. It is about a species standing at the bottom of a gravity well, burning thousands of tons of explosive chemicals every time it wants to move a few humans off the surface of one planet. Right now, the cost of lifting 1 kilogram to orbit is roughly $1,200 on the cheapest rocket humanity has ever built. The space elevator's projected cost is $57. That is not an incremental improvement. That is the difference between exploration and civilization. At $1,200 a kilogram, you can send scientists to orbit. At $57, you can send teachers, farmers, construction workers. You can build. The reason the space elevator matters is not that it is likely. It is that nothing else solves the fundamental economic problem of leaving Earth. So chemical rockets will always be expensive because they fight gravity with brute force. Nuclear rockets are more efficient but politically doomed. The United States just canceled its Draco nuclear propulsion program for the third time in 60 years. The space elevator is the only concept that converts the problem of gravity from an enemy into an ally, using Earth's own rotation to hold the cable taut. It is elegant in a way that no rocket will ever be. And yet, the material does not exist, not at the scale required, not at the strength required, not in the quantity required. We are closer than we have ever been. Single crystal graphene was impossible in 2016 and routine by 2024, but closer is not there. Obayashi says 2050. The International Space Elevator Consortium says the material could be ready in 5 to 10 years. Turan Google's engineers, who actually ran the numbers, said deep freeze and walked away. So here is my honest assessment. I did the math. The physics works. The engineering is plausible. The economics are transformative. And the material is not ready. It might be ready in 10 years. It might be ready in 50. It might never be ready. Because scaling a half-meter crystal to a 100,000-kilometer ribbon is not a manufacturing problem. It is a civilizational one. It requires a sustained investment in fundamental materials science that no government and no corporation has committed to making. The question I cannot answer, and neither can anyone else, is this: is the space elevator the greatest engineering challenge humanity has ever faced, or the greatest engineering fantasy it has ever believed? And the difference between those two things is not physics. It is willpower. And I want to know what you think. Are we building this, or are we dreaming it? Tell me in the comments. And if you want to know about the other technology that could make rockets obsolete, nuclear propulsion, which NASA just killed for the third time, that video is right here.